Swayam Prabha. Digital India. Educated India.
So, welcome back. I hope you all are enjoying the lecture so far in this open course on diffusion in multi-component solids. So, in the last class we went through the solution for diffusion equation for instantaneous planar source boundary conditions, and we saw it has applications in doping of semiconductors and also in determination of impurity diffusion coefficients in metals and alloys. So, today we will solve the diffusion equation for another set of boundary conditions, which is again industrially very important. It is encountered in one of the most commonly used industrial processes called carburizing and hardening. So, in many applications it is required that the steel has a very hard surface and tough core, so that it has a very good wear resistance as well as it can withstand the high impacts. Right. Some of the examples are all the transmission components that they use in a vehicle, like gears and shafts. They undergo this important what is called as surface hardening process, carburizing and hardening. So, there are various ways in which surface hardening can be carried out, and one of the most commonly used way is carburizing and hardening. So, in this process we start with a steel component which is made in low carbon steel. So, the component is manufactured in low carbon steel. So, to start with, the steel has low carbon content around 0.2 weight% throughout the component. Then it is exposed to an atmosphere which is rich in carbon, and it is heated to a high temperature. So, that there is a carbon concentration gradient from the ambience in atmosphere in the furnace to the the steel component, right. So, the carbon diffuses into the steel. Now, this is a diffusion based process. So, the depth up to which a particular carbon concentration can penetrate depends upon time and temperature, and also the diffusivity of the material. In this case, it is carbon in steel, and so it is very important to know to what extent a particular carbon content has penetrated, or to what depth we have achieved a particular carbon content for a given time, or we need to know how much time we need to do the carburizing at a given temperature to achieve the desired case depth. Usually, the depth up to which the desired hardness is achieved on the surface is referred to as case depth. There are various ways the manufacturers quote their or the manufacturer characterize their case depth. It may be in terms of hardness, or it may be in terms of the minimum required carbon concentration achieved at that particular depth. Okay. So, obviously, this depends upon the diffusion. So, if we want to design the heat treatment parameters for this particular heat treatment, we should have the knowledge of diffusion of carbon in steel, and then we need to solve the diffusion equation for this particular boundary condition, right. So, let us talk about this problem here. So, suppose this is the carbon component. Let us consider a carbon component in the form of a slab. On the left side is the carbon atmosphere, and we have thickness in the x direction, thickness of the slab. So, at the surface we have x equal to 0, and the components usually have a large thickness. So, that during the carburizing treatment the carbon does not penetrate all the way up to the other surface. So, we can maintain the infinite boundary condition. So, in this case x varies from 0 to plus infinity. So, this is called semi infinite slab. So, semi infinite slab boundary condition. The heat treatment is usually carried out and the atmosphere is maintained such that there is a constant carbon concentration at the surface. So, at the surface the concentration, let us denote it by Cs, and typically steel will have certain carbon concentration to start with. To make the problem simple initially, let us assume the carbon concentration in the steel before carburizing is 0, right, and since we are maintaining infinite boundary conditions. So, at the other end the carbon concentration will always remain C 0. Okay. So, we have to solve the diffusion equation dou C by dou T equal to D times dou 2 C by dou x 2 with the initial condition that the concentration at any x at time t equal to 0 is C 0, and in this case C 0 is 0 for all x greater than 0. And what are the boundary conditions? At the surface carbon concentration is always maintained as Cs. So, C at x equal to 0 at any time t is equal to Cs, and the second boundary condition is at the other end the original concentration of steel remains. In this case we are assuming it is 0. So, C at plus infinity at any time t is equal to 0. So, we have to solve this diffusion equation with respect to this initial and boundary conditions. Okay. So, let us use the Laplace transform just like we used it last time. So, if in the diffusion equation if we multiply both sides by e to power minus k t and integrate from 0 to infinity, d is constant. So, let us take out of the integral 0 to infinity e to power minus k t dou to c by dou x 2 dt. So, there should be this term dt. Let us first solve the left hand side. LHS is equal to integral 0 to infinity e to power minus k t dou c by dou t dt. We can solve this integral by integration by parts, and we know the formula for integration by parts. Integral a to b u dv equal to u v from a to b minus integral a to b v du. So, if we look at the integrand here, we can assume u equal to e to power minus k t and dv equal to dou c by dou t dt. So, that du becomes minus k e to power minus k t dt, and v is nothing but c. So, by solving integration by part we get LHS is equal to u times v. So, c times e to power minus k t from 0 to infinity minus integral v du, v is c and du is minus k e to power minus k t. So, two minus sign will get cancelled, plus k is outside the integral because it is constant, not dependent on time. So, k integral 0 to infinity e to power minus k t times c dt. So, if we evaluate, remember these limits are for time. So, t equal to 0 to t equal to infinity. So, at t equal to infinity, e to power minus k t will be 0, and c at infinity, at t equal to infinity, obviously it will have a finite value, right. In this case it is 0. So, this first term will be 0 minus at t equal to 0, the exponential minus k t becomes 1, and at t equal to 0, c 0 will be 0, right. So, c naught is 0, c at t equal to 0 at any x is 0. So, the first term becomes 0 plus the second integral is nothing but the Laplace transform of c of x t. So, it is k c bar. So, our LHS comes out to be k c bar, where c is the Laplace transform of function c. Now, let us look at RHS, which is equal to d integral 0 to infinity e to power minus k t dou to c by dou x 2 dt. Just like we did for the previous problem, e to power minus k t is independent of x. So, we can take it inside the differential, and then we can change the order of differential and integration, which would yield d times d dou 2 by dou x 2 of integral 0 to infinity e to power minus k t times c dt. And again this integral is Laplace transform of c. So, we can write RHS is equal to d dou 2 c bar by dou x 2, and c bar is now not dependent on time, and so we can replace partial derivative with ordinary derivative. So, RHS becomes d times d 2 c bar by d x 2. So, we get k c bar, which is LHS, equal to d 2 c bar by d x 2, and if we rearrange, we get the ordinary differential equation in c bar d 2 c bar by d x 2 minus k by d c bar equal to 0. So, again we have seen, just like the last problem we solved, Laplace transform has helped us to convert the partial differential equation into an ordinary differential equation, which we can easily solve here. And the solution for this may be e to power lambda x. If we substitute back, we get lambda square e to power lambda x minus k by d e to power lambda x equal to 0. So, we get lambda equal to plus minus square root of k over d, and if we have multiple solutions, the linear combination of the solutions is also a solution. And so, we can write c bar equal to p exponential minus root k by dx plus q exponential plus root k by dx. Now, we have to find out these constants p and q. One constant we can straight away eliminate. Which one is that? Q, right, because our x is varying from 0 to plus infinity, and we want the concentration field to behave at all x, including at x equal to infinity, which is possible only if q is 0, right. So, q is 0. So, we are left with only one term, c bar equal to p exponential minus root k by d x. Now, to get the value of constant p, let us use the boundary condition, which is C at x equal to 0 at any time t is C s, right. And if we take the Laplace transform again from on both sides, integral 0 to infinity e to power minus k t C of 0 t dt equal to integral 0 to infinity C s is constant e to power minus k t dt. And so, C bar of 0 is equal to C s time e to power minus infinity is 0, e to power 0 is 1, and there will be a term in minus 1 by k. So, C bar at 0 we get as C s over k. So, if we substitute in the equation that we got for C bar here, we get the value of p as C s over k. And so, the solution for C bar is equal to C s over k exponential minus root k by d x. So, now if we take x by root d as a, we can write C bar equal to C s time 1 over k exponential minus a root k, and this looks familiar, right. We solve this Laplace transform. So, if we take the inverse Laplace on both sides, we get our concentration field. So, C is equal to C s is constant L inverse of 1 by k exponential minus a root k. And if we look at the Laplace transform table, or we solved this in a previous class, the Laplace transform of this term is error function c, the complementary error function a over 2 root t. Error function c of x is nothing but 1 minus error function of x, and a in our case is x over root d. So, we get the solution for concentration as C is equal to C s into 1 minus error function of x over 2 root dt. So, this is the solution that we have obtained for a semi infinite slab with constant surface concentration, which is typically encountered, for example, in carburizing of steels. Okay. So, let us look at some of the features of this solution. Right. So, if we draw the plot of carbon concentration versus x or versus depth into the surface, how should it look like? So, if we know the curvature and the slope, we can get an idea of the plot, right. So, if we evaluate the slope, which is nothing but the derivative, so dou c by dou x will be C s is constant. So, dou C s by dou x is 0 minus dou by dou x of error function x over 2 root dt, and we know the derivative of error function. What is it? D by dz of error function z is equal to 2 over root pi exponential minus z square. So, in this case dou c by dou x equal to minus, so we have to also differentiate this 1 over 2 root dt into 2 over root pi exponential minus x square over 4 dt, which is basically this 2 will get cancelled, 1 over root pi dt exponential x square over 4 dt minus x square, should be a minus sign here, and then again there is a minus sign here outside. So, minus 1 over root pi dt exponential minus x square over 4 dt. So, the slope will be negative, right, because the exponential term will always be positive. Now, let us look at the curvature, which is the second derivative, that should be minus 1 over root pi dt times minus 2x over 4 dt exponential minus x square over 4 dt, and so is equal to 2x over root pi times dt to the power 3 by 2, and there is also a factor of 4 exponential minus x square by 4 dt. So, the curvature is positive. What it also means that if we look at the diffusion equation, right, dou c by dou t equal to d times dou 2 c by dou x 2, the curvature is always positive at all x, which means dou c by dou t is positive. So, the concentration at any x position should increase with time. If we try to plot concentration versus x at any given time. So, if Cs is the start composition on the surface, negative slope and positive curvature. Right. So, if we plot at different times, you know that this concentration at the surface should always be constant, and at other x the concentration should increase with time. Okay, so this is how the concentration plots would look like. Now, again if we look at the solution carefully, c equal to Cs 1 minus error function x over 2 root dt. In this, on the right hand side, if you see Cs is constant and d is also constant. So, the concentration we can see is a function of x over root t. Right. So, what does this mean? Our concentration here is a function of x over root t. This x over root t is usually referred to as Boltzmann parameter lambda of c. So, each concentration plane here is a function of lambda or x over root t. What does it mean physically? So, if we track a particular concentration, right, So, let us see if we want to track the concentration C I, the depth at which the concentration is C I at different times, right. Let us say then T 1, T 2, T 3 here, and let us denote the depth at which we see C I as x 1, x 2, x 3 at T 1, T 2, T 3 respectively. What this relationship tells me is that x 1 by root T 1 equal to x 2 by root T 2 equal to x 3 by root T 3 and so on, is a constant lambda, which is a function of C I. This is a very important consequence, because it helps us to roughly estimate the case depths once we design a process for a particular component for a given case depth, right. And suppose we want to change the case depth for that component as let us say required by the customer, then we do not have to again go back and do the redesign. If we have the same steel component and we do the heat treatment at the same temperature, so same temperature means basically D is constant. So, we can straight away use this relation and decide the case depth, right. So, for example, if we had designed the process for a case depth of 500 micron and let us say, so x 1 is equal to 500 micron and the carburizing heat treatment time for the, attaining the 500 micron case depth was let us say 4 hours. But now we want to design the process, or we want the case depth of 1000 micron. So, what should be the heat treatment time? So, if we substitute here 500 by root 4 is equal to 1000 by root T 2. So, root T 2 is equal to 2 times 1000 by 500, which is 4. So, T 2 is 16 hours. So, this is important, because what this tells me, if I want to double the case depth, I need to increase the time to 4 times. So, there is a x by root T relation, it is also called as parabolic relation. So, we say each concentration plane moves parabolically with time, has a parabolic relation with time. Now, another point I would like to note here is we are maintaining infinite boundary condition, right, which again means that the diffusing species is not penetrating all the way to the other surface. But is it really true in practice, or can we estimate for the given thickness of the plate, can we maintain the infinite boundary conditions? Right. So, for that, if we look at, so this is a typical error function solution, right. C is equal to C s 1 minus error function x over 2 root d t, and we want basically the distance at which concentration drops to the original concentration, that is 0, right. And from this equation we will see that is where the error function x over 2 root d tends to 1. Now, mathematically what is the value of z for error function z to be 1? Infinite, right. That means that is what that is why it is infinite boundary condition, but physically let us see, if we look at the error function, error of x versus x curve, right. This is the plot of error function x versus x, and we know error function infinity tends to 1. But if you closely look at the plot, this plot kind of flattens out or levels approximately to 1 even at x equal to 2, right. So, we can approximate even when x by 2 root dt is approximately 2, we will get the original composition, right. So, that is where x by 2 root dt is equal to 2 or x is equal to approximately 4 root dt. So, that is one rough measure to see if the given thickness of plate and time can satisfy the infinite boundary condition, right. So, the thickness has to be at the minimum 4 root dt, of course, more than that. So, to be safer, we take maybe 6 root dt or 8 root dt minimum thickness, and typically the component thicknesses encountered are much larger than the case depth. So, this infinite boundary condition will always be satisfied. So, we derived an equation for evolution of concentration profile in a semi infinite slab boundary condition, and which takes the form of C equal to C s times 1 minus error function x over 2 root dt. Now, we derived this equation assuming that C 0 equal to 0, that is this concentration of the species in the slab to start with was 0, or when we talk about carburizing, this solution assumes that the initial concentration of the steel that is being carburized is 0. However, this is not the case in practice. As I said, the steel that is going to undergo carburizing heat treatment is a low carbon steel. So, it has some carbon concentration, typically around 0.2 weight % carbon. So, how do we solve the diffusion equation in this case? It is simple, we just need to rescale our concentration axis. So, if we look at the problem, to state the problem, we have a semi infinite slab whose initial concentration is denoted by C naught is C naught, and the surface concentration which is maintained constant during the process is C s, and we have to solve the diffusion equation dou C by dou T equal to d dou 2 C by dou x 2. Now, C naught is not 0 in this case. Right. So, the initial conditions are C at any x at t equal to 0 is equal to C naught for all x greater than 0, and the boundary conditions are C at x equal to 0 at any time t is C s, and since we are maintaining infinite boundary conditions here, so the surface is x equal to 0, and the other end we denote as x equal to plus infinity. So, C at infinity at any time t is the original concentration, that is C naught. Now, we make a little bit of substitution here. Let us call C prime is equal to C minus C naught, and C naught is a constant. So, d C prime is nothing but d C. So, our diffusion equation with the new modified concentration variable becomes dou C prime by dou T equal to d time dou 2 C prime by dou x 2, and the initial condition becomes C prime at x naught is equal to C naught minus C naught, which is 0, and the boundary conditions become C prime at x equal to 0 at any time t is equal to C s minus C naught, which let us denote it as C s prime, and C prime at infinity at any time t is again C naught minus C naught equal to 0. So, we got back the diffusion equation and the initial and boundary conditions in the form that we have already solved, right, and the equation for the concentration profile in terms of C prime would be C s prime into 1 minus error function x over 2 root dt, and if we substitute for C prime, it takes the form C at any x and t minus C naught divided by C s minus C naught is equal to 1 minus error function x over 2 root dt. So, this is the more popular form that you will see in most of the textbooks, right, and this is applicable for a semi infinite slab which has an initial concentration equal to C naught. Okay, and this is more applicable, more practically applicable to the carburizing problem. All right. So, with this we will stop here for today. Thank you.